For today's class, we're going to look at the chain rule. So far, we've looked at just straight derivatives of polynomials. We've looked at the product law. We've looked at the quotient law. But what happens if you have a composition of functions, right? Think back to when we're doing grade 12 advanced functions, and you had one function being composed into another function. And if you look at the screen, you see that I have an example of that here. We have two functions, an f of x function and a g of x function. If I were to compose the g into the f, that would refer to as the FOG. So it's the f of the g. It really means putting the g into the f. So if you could just sort of look at where my mouse is pointing to, sort of try to figure out where I'm trying to focus your attention. The g function is this function here, the 4x6 plus 5. I'm going to put that wherever I have x in the f of x function. That's what g into f represents. So I'm taking the 4x plus 6 plus 5, and I'm basically squaring it. And if I wanted to continue that, I could just simply square the first term, which gives us a 16x to the power of 12, multiply these two terms together, which would be 20x to the power of 6, and doubling it. That's how we square a binomial. And then we square the last term. That's where these three terms come from. So the f of the g of x for these two functions turns out to be what you see here, 16x12 plus 40x6 plus 25. It's not the same going the other way because composition is not what we call commutative. So the g of the f means putting the f into the g. So here's our f function. I'm going to put that where the x is in the g function. So this x to the power of 6, I'm going to put the x in place of the x here. So what I have is 4, the x squared function, being raised to the power of 6 then plus 5. And if you follow that through, you're going to get the 4x12 plus 5. And clearly, these two compositions are not the same. So just a quick review of composition of functions. Let's move on to what the chain rule for derivatives is. Now, this might look like a lot of Greek right now, that if I have an f of the g of x, and I'm trying to find the derivative, then it is what you see here. It looks like we're multiplying two things together. It looks like we're multiplying the inner function derivative by the outer function derivative. And that's exactly what it is. In Leibniz's notation, and this will become very clear when we do our first example in a minute, if y is a function of u, and u is a function of x, then if we want to find dy dx, remember that the function that we have between y and u is one function, and then there's another function between u and x. That's a second function. But what I really want to know is the relationship between y and x. That's what my dy dx is. So if I took my dy du, which is when I'm differentiating y with respect to u, that's what dy du is, and multiply that by du dx. I'm differentiating the u function with respect to x. If I multiply those two together, then if you think about it, what's going to happen is that we're going to have this being cancelled out with that, and we're left with dy dx. That's exactly what we want. So that is the essence of the chain rule. When you multiply two derivatives together, you end up with the derivative that you really want, which is the relationship between y and x. That will become hopefully more clear on our first example coming up on the next page. All right, so let's take this function as y equals 3x squared minus 2x to the power of 5. That's the function. But let's separate it and pretend as if we have two relationships between u and x, and then between y and u. Meaning, if I took this part here, right, and let that part be u, then that would mean that the y function would become u to the power of 5, because this part here is replaced by the u. So it means that this becomes u to the power of 5. So just think about that for a minute. This 3x squared minus 2x is my u here. And if I raise u to the power of 5, then I essentially have the same y equals 3x squared minus 2x to the power of 5. This is a direct relationship between y and x, whereas this is a relationship between u and x, and this relationship between y and u. But just to bring it back to the previous slide, I can now find dy du. What do I mean by that? I'm going to differentiate this function here as this function here is dy du. dy du is the derivative of y with respect to u. This function over here would be my du dx. I can find this derivative as well. So dy du, if you sort of focus down here now, is taking the y equals u to the power of 5 and deriving that. Well, there's your 5u to the power of 4. We know how that works. That's just a simple polynomial type of derivative. Then we're going to derive u with respect to x. So u with respect to x would be the 6x minus 2, which is what this is right here. So this is dy du. This is deriving y with respect to u, because remember, u is equal to this and y is equal to this. So if I just simply take dy du, then I have 5u4. If I take du dx, that would be 6x minus 2. So these are two separate functions that seem to have two different variables. But I have a dy du and I have a du dx. If I multiply both of these together, as it says in this box right here, then I should end up with a direct relationship between y and x. So I'm taking my 5u4, which is the dy du, and multiplying that by my du dx, which is 6x minus 2, these two things here. And this should be my dy dx. Now, you might be wondering, well, this function seems to have a u in it. Well, we know what u is. We had that u was equal to 3x squared minus 2x. So we can replace that down here. And now we have a function that is strictly between x and y. So here's your u function being substituted back into your derivative. So you have the 5, the u function to the power of 4, and then you multiply by that the derivative of the inside function, which is a 6x minus 2. These two together represent the derivative of the original function with respect to x, right? So you take the derivative of the outer function, multiply by derivative of the inner function. Hopefully that makes sense. You can slow that down, review that, go over that again, just to make sure that all makes sense. At some point, we may not need to make the substitution because we will understand that we're really deriving the outer function and then multiplying it by the inner function. So as we go through the next example, you'll probably see what I mean by not having to make this substitution explicitly, but it's sort of implied in what you're doing. Okay, so here's the example I'm talking about. We're going to apply the chain rule to this. So this is our inner function. This is like what we would have called u in the previous example, x squared minus 5. But I'm going to leave it as just x squared minus 5. And we're raising that to the power of 7. So the first step for dy dx is to take this part here and derive it. So meaning the whole thing which is being raised to the power of 7, which would therefore become 7 times this inner function raised to the power of 6. And then we multiply this now by the derivative of the inside function, which would be the 2x. So this whole thing represents your derivative. Let me go over that again. Take the derivative as if this was a u. So it would be 7 times u to the power of 6, which is what this is. Then we multiply that by the inside, which is the derivative of x squared minus 5, which is 2x. So this is your derivative, and then we can just tidy that up a little bit by multiplying the 2x by the 7. So we have 14x x squared minus 5 to the power of 6. And I do expect you to simplify things as much as possible. That is an easy example of simplification. There are going to be some where the algebra that is involved in simplifying is a little bit more involved. But for this one, that's just multiplying the 2x by the 7. Okay, let's take that to a little different level, a little higher level, by looking at an exponent which is not just regular integer, such as 1, 2, 3, 4, or 5. This was 3 over 2. So it's a rational exponent. Well, we still apply the principle, which is to multiply first of all, derive the inner function, or the outer function, I should say. So that would be 3 over 2 times this to the power of 1 minus that, which is what this is. So there's 3 over 2, x squared plus x to the power of a half. So 3 over 2 minus 1 is a half. Then we're going to multiply that now by the derivative of the inside. Well, the derivative of the inside is the 2x plus 1, which is what we have here. And yeah, I'm not going to make a big issue of it, but it's not a bad idea for us to restate this thing, which is raised to the power of a half, as a square root, which is really what an exponent of a half is. So I've chosen to write the final derivative as 3 over 2 times 2x plus 1 times the square root of x squared plus x, which represents this part of the derivative right here. Okay, so fairly straightforward, just that we're dealing with an exponent, not an integer. How about if we had two distinct functions this time, one in terms of u and one in terms of x? So this is your relationship between y and u. This is your relationship between u and x. They're asking for a derivative that relates y to x. What is that derivative? And then they ask for us to state what that is at a particular x value. So clearly there's a relationship between y and x, but it is sort of through a link that you have between the two of them. This is like the composition that we talked about earlier. So we need to take dy dx, as we said 2 slides ago, and to get dy dx, we have to take dy du and multiply that by du dx. So we're going to derive this function with respect to u, and we're going to derive this function with respect to x. Okay, let's start with dy du. This is simple enough. This is just the normal run-of-the-mill kind of derivative, which should get 3u squared minus 2, which is what this is. So that's your derivative of y with respect to u. And then we're going to find the derivative of 2 square root of x. Now remember that the square root of x is the same thing as x to the power of a half. So I've in fact written it as x to the power of a half, or that's sort of implied. And then I'm going to multiply the half by the 2, which is what's down here, and then raise that to the 1 minus a half, which is what we have right here. Again, this easily simplifies. The 2 times a half is 1, and then x to the minus a half is the same thing as 1 over the square root of x. So this represents the du dx. That's your second derivative. So your first derivative is the 3u squared minus 2. And your other derivative with du dx is the 1 over the square root of x. So those are two derivatives that are relating two variables. And now we have to combine them by multiplication. So remember that the dy dx is the dy du multiplied by du dx. That's what's up here. So that's what the next line is going to say. We have the 3u squared minus 2. That's this line. And we're multiplying that by 1 over the square root of x, which is this line. So what we have now is a derivative. And the question is, do we need to actually make the substitution so that we have just x in the function? Because remember, we wanted dy dx. That's our goal. Well, the question didn't actually ask us for dy dx. It was specific about what they wanted. They wanted when x was equal to 4. So you could get away with actually figuring out what u is when x is 4 and then putting that in the u into the function without having to actually substitute the actual function that relates u to x. That's what we're going to do. So since u is equal to 2 square root of x, that was the original relationship between u and x. When x is 4, then u is equal to 2 times the square root of 4, which of course is 2. So 2 times 2 is 4. So it turns out that when x is 4, u is also 4. So what we can do now is we can substitute for both x and u into the dy dx function and get an answer. So here's what the next line says. When x is 4, we're putting 3 times into the derivative, 3 times the 4 squared minus 2 multiplied by the 1 over the square root of 4. All right, that's your derivative with the u and the x being substituted with 4. They're both just coincidentally 4. That's not always the case, by the way. So here we go. A little bit of algebra. We could get that this is 46 times a half, or 23. And that's your derivative when x is equal to 4. Well, let's put that to use in an application. We're looking at the relationship, two different relationships. This question talks about the relationship between the carbon monoxide level and the population. It sort of is suggesting that the bigger the population is the more emissions that you have, which kind of makes sense from what all we're hearing about emissions. So we have that relationship between the population and the carbon emissions. By the way, carbon emissions being measured in parts per million. And we also have another relationship between time and population. That's the second relationship that we have here. And what we're being asked to find is what's the rate of carbon emission in 3 years. Now remember, we don't have a direct relationship between the carbon and time, but we do have a link because one relates carbon to population and one relates population to time. So one approach is that we could actually just use a composition of functions strategy and put this time versus population function inside of this function here. That's one approach that we could take. But we're just going to use a chain law, right? And the chain law says if we want dc dt, which is what we want, then we're going to take the dc dp, remember that's the relationship between population and carbon emissions, and multiply that by dp dt, that's the relationship between population and time. And if we multiply those two relationships together, we should end up with the dc dt relationship, which is ultimately what we want because we're trying to ask the question of the rate of emissions with respect to time. So in 3 years from now, what's the rate of emissions? So we're going to do that. We're going to take the dCdP. So here's the first derivative, the dCdP. So here's your relationship between carbon and population. And you know what we have to do, raise that to the power of a half, and then it's a half times the inner function raised to a half minus 1, which is minus a half, multiplied by the derivative of the inner function. So that would be the 2 times the 0.5, which is just p. So this is using that chain law that we just talked about itself, right? So that's the actual application of the chain law right there. So that, if we do a little bit more algebra, put this thing that has a negative exponent as a denominator and leave that denominator of 2 there and the numerator of p on top. So this is a relationship between population right here and carbon emissions. That's what this relationship is. That's what this derivative is meant to show. So let's now find the derivative between population and time. That's a simple one because that is just simply this. And the derivative of this, that's dp dt, is just this, 0.2t. So now we're going to multiply these two together. So we're going to take this derivative and multiply it by this derivative. And if you think about it, I'm just going to say 0.2 TP, okay? Just multiply these two together, and that's over 2 times this. All right? Okay, so the question now is very specific. It didn't ask us for a DP, or a DC DT relationship. It didn't ask us for that in general terms. It asked us in a specific way for what happens in 3 years from now. So again, like in the previous question, we can get away with just simply asking the question, what is the population in 3 years? And then we can use that value of P in our derivative. So down here, we're going to do exactly that. We're going to put the 3 into the population equation, which is what I'm doing right here. And it turns out that the population in 3 years works out to be 4. I believe that's 4,000. I believe population was being measured in thousands. Yeah, that's in thousands. So that's 4,000 people. So take that as 4 into the derivative that we had of dc dt with a t value of 3 and a p value of 4. Remember when in 3 years we have 4 as the population. So this is the time, this is the population, and this is the derivative. We're putting it all together. Anywhere we saw the p, we put the 4. Anywhere we saw the t, we put the 3. And that's what this looks like. So if we just do the math on that, it works out to be this, which is 0.24. And that, of course, needs proper units for us to interpret it. That's a CO level rising at the rate of 0.24 parts per million per year. Remember, we're relating emissions to time. So that's 0.24 parts per million per year in 3 years. That's the rate at which it is rising in 3 years. Okay, let's now look at what happens when we combine this chain rule that we've just learned with the product rule that we learned 2 days ago. We're going to take this function, which is a product of 2 functions, and we're going to derive it. So remember how that works. We're going to derive the first part and multiply it by the underived second part. That's the product law. So This is an application of the chain law. So that would be 4 times this to the power of 3. That's what the first part of this is. Times the inside function, which is a 2x. That's what we're doing here. Multiplied by this second part on the right. So that's just going to be 4x minus 5 to the power of 3. That's all that is. Plus, we're going to now take the 4x minus 5 to the power of 3 and derive that using the chain law. So it's 3 times that to the power of 2 times the root of the inside, which is the 4, times the underived last part, or well, actually the first part of this equation, x squared plus 3 to the power of 4. So this whole thing, this plus this, that's your derivative. Now I'm expecting more from you, so I'm going to walk you through the algebra of simplifying this so that when we have a question like this, you know exactly how to proceed. We're going to have to try to find a common factor between the first part and the second part. Well, before we do that, let me just do a little bit more simplification. The 4 and the 2x gives me 8x. The 3 and the 4 gives me 12. So that's all this is. I haven't done anything more spectacular than that to go from the first line to the second line. But to get to the third line, let's come up with the common factor of these two terms. Now, let's start with the coefficients. You can call them coefficients, the 12 and the 8x. The common factor between those two is 4, right? So that's why that's part of my common factor. This has a 4x minus 5. This also has a 4x minus 5. This one is to the power of 3. This one is to the power of 2. So the common factor would be the smaller exponents between those two terms. So I'm going to use 4x minus 5 to the power of 2, you see me pointing to it here, as part of my common factor. There's an x squared plus 3 to the 3. There's an x squared plus 3 to the 4. Same principle. Use that as part of your common factor, but to the lower of the exponent. So that would be x squared plus 3 to the power of 3. So that's why all of this represents my common factor. The 4, the common factor between these two. Then there's the 4x minus 5 squared and the 4x minus 5 cubed. So I'm going to have 4x minus 5 squared as my common factor. There's an x squared plus 3. So there's an x squared plus 3, 4x squared plus 3. I'm going to use x squared plus 3 to the power of 3 as my common factor. Now, watch what we're going to have to do. Divide this common factor into all of this first part here. Well, the 8x divided by the 4 is 2x. So that's why there's 2x here. So that's 8x divided by the 4. That's my 2x. If I divided this now by all of this, the x squared plus 3 and x squared plus 3 will cancel each other out. But when I divide 4x minus 5 to the 3 by 4x minus 5 to the 2, I'm going to still have a 4x minus 5 left. And that's why you have this here. So that's 2x times 4x minus 5 plus, okay, we're going to divide this second part now by the same common factor. So the 12 and the 4 divides to give me 3. There's the 3 right there. The 4x minus 5 to the 2, there's a 4x minus 5 to the 2 in the common factor. Those cancel each other out. But this x squared plus 3 to the power of 4 and this x squared plus 3 to the power of 3, which is part of my common factor, I'm still left over with an x squared plus 3 to the power of 1, which is what this part is. So here we go. We have the 2x times the 4x minus 5 plus the 3 into x squared plus 3. All of this represents a common factor. You may want to rewind that part and just look that over again to be clear on how we got from all of this to this. But then we have to do a little bit more work, which is to multiply this out. So multiplying the 2x into the 4x minus 5 gives me 8x squared minus 10x, and the 3 into the x squared plus 3, so 3x squared plus 9. And then it's just a matter of putting like terms together. So this is my common factor. My like terms in this bracket gives me 11x squared minus 10x plus 9. Okay, one more. Let's try to derive something that has a quotient. So we're going to have to use the quotient law this time. And of course, the chain law as well, the thing we just learned. Part of it is using the chain law and the quotient law. So first thing I'm going to do is I'm going to use that chain law. This is to the power of 10. So according to the chain law, I'm going to take 10 times the inside part raised to the power of 9. Then I'm going to have to find the root of the inside part. The root of the inside part is a direct quotient law application. So the root of the top, 1 plus x squared, is a 2x, multiplied by the underived denominator. So 1 minus x squared. So 2x times 1 minus x squared minus, there's your quotient law, the derivative of the bottom, which is minus 2x, multiplied by the underived top, so 1 plus x squared. So all this is just the quotient law, of course, over the denominator squared. So over 1 minus x squared squared. All right? So I'm just going to now continue that by still writing the 10, 1 plus x squared, 1 plus x squared to the power, and that's still there. But then I'm going to expand this. So the 2x times the 1, 2x times the minus x squared. The minus, that's really just plus. So plus 2x plus 2x cubed. Fortunately for us, these two will cancel each other out. The minus 2x cubed and the 2x cubed will cancel each other out. And we have some like terms here. We have a 2x and a 2x. So that's 4x. That leads us to this line. So I have a 4x on top over the 1 minus x squared squared. So that would be your quotient law application here. Don't forget, I still have this part here that came from the chain law. That was always there. It was always on every single line. It was always there. There it is. There it is. And it's still here. So now we're going to try to combine these two together, right? This is on top. Think of the 10 as being 10 over 1. So 10 times 4x, of course, is 40x. I have the 1 plus x squared being raised to the power of 9. Think of it that way. The bottom is also 1 minus x squared to the power of 9. A numerator and a denominator, if you have a quotient being raised to a power, then both the numerator and denominator get raised to that power. So 1 plus x squared is being raised to the 9, but 1 minus x squared is also being raised to the power of 9. Now notice what happens when I multiply these two together. The top, of course, is still just the 40x, and the 1 plus x squared to the 9 is still there. But the bottom, they really have the same base. 1 minus x squared to the 9, 1 minus x squared to the 2. And the rule of exponents says that I don't have these two things that have the same base. I can just simply add those exponents together, which is what this is. So I have 1 minus x squared to the power of 11. So the top of this is the 40x, 1 plus x squared to the 9, and the bottom is 1 minus x squared to the power of 11. And yes, I am expecting you to be able to follow the algebra through to that point. And that's about it. I expect you to be able to derive anything that we saw in today's lesson, including the one that's in your success criteria. You can think about how you do something like that. It's not that difficult. It's your quotient law, it's your chain rule. All of that is involved right here.